sharing the story of my background. In high school, I wrote this baseball game, and I kept getting feedback from folks who played it on sort of how I can improve the game, and that's kind of how software development was for since the dawn of ages for 30 or 40 years, right? You go in and you manually make changes, and heuristics and rules of thumb were the ways that you improved a given program. Next slide. So machine learning is using many examples to answer questions. So machine learning changes that paradigm of how software is developed. Instead of going in and manually making changes, instead you use lots and lots of examples to answer some of these questions, like what's the best experience for making a baseball game that's more realistic. I probably should start at the top here and say the first half of this presentation is sort of a machine learning and AI 101. So for those folks who already know this, you could skip, if you're watching this later, 10 or 15 minutes forward to the second half, which is really the practical applications of AI and machine learning. But for other folks who maybe don't want to hear much of a product pitch, just listen to this first half. So machine learning is using many examples to answer questions. So next slide. So what does that mean practically speaking? Machine learning is data and algorithms that provide insights or another way of saying it, it's statistics plus programming to make those predictions. Again, using those examples to make predictions, because heuristics don't scale well. So you can imagine it's fine for me going back and making individual changes to my baseball game over and over and over again. But now fast forward to a global, hyperscale company like Google with millions and millions of lines of code and billions of users. And these changes happen at such a velocity, it becomes impractical to continue to hire developers to make these manual heuristic changes. Next slide. So machine learning and AI, the hype is just ridiculous right now. We are at the peak of inflated expectations, and I guess one of the most common questions I get asked is why? Why is there so much hype today versus 5 or 10 or 15 years ago? Next slide. And I think it's a combination of three things. And there's a build on this. There we go. It's three things that are available today that maybe weren't available in the past. The first is data. High quality data sets exist today in a really unique and compelling way. The second thing is compute. And the third thing is tools or frameworks. So let's talk about each of these very quickly. So the first one, next slide, high quality data sets. So I think we all know about big data and the increase in volume and velocity and variety of data. And this stat was, I think, from IDC saying in 2025 there'll be 10 times the amount of data that exists today, 50 times the amount of data that's subject to data analysis, and 100 times the amount of data that's touched by cognitive systems. And remember, data are the examples that machine learning needs to be able to make those predictions. So data everywhere. This is a change. Everybody's got cell phones now. IoT data collection is becoming a reality. Of course, everything that happens on the internet generates data. So data is everywhere. Next slide. Second thing is compute. So it turns out that to do the training for machine learning is actually computationally intensive, but it's a slightly different type of computation. So neural network mathematics closely resemble the algorithms in GPUs. So it's a different type of math. It's matrix math. And so with the advent of GPUs for things like gaming and graphics, suddenly you've got these ASICs that are more efficient in doing the training. So again, driving down the cost and increasing the speed. Second thing is custom ASICs have been developed, not just by Google, so TensorFlow processing units, but by other hyperscale vendors that are specifically built to do this type of math. And then the third thing is the group that I work with is cloud. So we have cloud scale, and cloud economics is a reality. So only use what you need, scale as you need it, scale infinitely or semi-infinitely. So there's lots and lots of advancements in compute that's ultimately driving down the cost of doing training and driving down the cost of improving these models. So the first thing is data, second thing is compute, and then the third thing, next slide, the third thing are improvements oh, this is an example of a TPU, a TensorFlow processing unit in a Google data center that's custom built to do this high speed processing. So these are things we rolled out a few years ago that are just these massive improvements in how quickly you can do training. Next slide. The third thing are these improvements in frameworks and tools, and this would not have been possible without the increased amount of data, the examples. It would not have been possible without the lowering the cost of compute, of training. But with those two things, the improvement in the research by researchers across the globe and also hyperscale companies like Google and Facebook has been dramatic. So there's some incredible breakthroughs on sort of understanding how the brain thinks and the idea of reinforcement learning and deep learning, so that you really have this virtuous circle of more and more data, cheaper and cheaper compute, and then better and better frameworks. Those are the three things that are driving machine learning AI today. Next slide. So quick example of that, this is deep learning, which is really where a lot of the innovation is. There's AI, machine learning, and the type of machine learning is just deep learning. So this is an image, it's just a picture of a cat or a dog. And each of these dots, we hear about these different layers in deep learning, represent effectively what we call a neuron, which is again a mimicking sort of how the brain thinks. But really what it is, it's simply a mathematical equation. And in the mathematical equation, there's weights. And those weights represent a best guess based upon examples. And each time you get more and more examples, those weights can change so that you have better and better results. So again, you have examples that give you predictions, those results. And so you keep going through these multiple iterations of training, and those weights get adjusted, and ultimately you end up with a prediction that is close to being accurate or perfect. So next slide. So this is what it would look like for an image. So this is the classic example of DeepMind. So this is, again, you have the input, which is pixels in and joystick out. These are just neurons making decisions, right? There's weights on it, and in 10 minutes of training, it's just how this game's played. It's just random luck, right? It doesn't have enough feedback yet to be able to really have any great insights. Next slide. But as you keep training, you skipped ahead too. But as you keep training, I guess that's right. At 120 minutes, basically, it plays flawlessly. So it knows that the outcome that it's trying to optimize for is score, and it knows that by moving the pixels, by moving the joystick in a way, it can increase the scores to be able to never miss. So it plays flawlessly after 120 minutes. The next slide is what's really astonishing is after 240 minutes, an actual strategy emerges. It recognized a strategy, which is if you can hit it behind, up across the top, that's the fastest way to optimize the score. So the strategy piece is what's really remarkable. It developed its strategy on its own based upon playing enough times to know how to optimize that score in the quickest amount of time. So next slide. So if that gameplay, which is something most people I think understand, is sort of the generalized AI of learning, grounded in reality and getting active feedback. So this is the DeepMind algorithm that could play 50 different computer games and can optimize for the performance. Basically again, based upon optimizing for the score and getting feedback when that score, when they crash, that's a bad thing. When they stay in between the lines, that's a good thing. So this is really remarkable. It develops strategies, again, through examples, through learning, to be able to improve outcomes. So next slide. If you were to fast forward to today, you could see in Waymo, you've got 10 million miles driven, and 7 years later, the blind drove a Waymo vehicle. So this application in a gaming world, you could see being applied in a whole variety of things, not just at Google, but in the rest of the world. Next slide. So some examples, I I talk a lot about AI, and I've got a set of examples that's literally, I don't know, dozens and dozens long now. Google Photos is a, you know, the classic example. Anybody who uses Google Photos now knows how great it is at identifying things in those photos. Again, because there's lots of examples of what a person looks like, or what running looks like, or what a cat looks like, or what a sunset looks like, and it's really quite remarkable. You can identify things in pictures that you didn't know were there. You know, a painting on the wall behind you that has the Eiffel Tower in the painting, and you'll search for Eiffel Tower, and it can identify that. So pretty remarkable. Again, lots of examples with good predictions. Next slide. Translates another example, right? The more translation examples you have, the better you can, the better your results will be. And so this is an iterative process. If you have that data, if you have those examples, you can get better and better predictions. Next slide. We've even applied this across search, and this is, you know, obviously something that Google's well known for. And RankBrain is a deep neural network for search rankings, and it's one of the top signals that has improved quality. This is quite remarkable. Again, when you look at the search for something like giants, if you type in giants in the search engine, you know, depending on the context of where you are and what other search results have been optimized, you know, you could be asking for really big people, or you could be asking about, you know, the San Francisco Giants or the New York Giants, or another sports team named the Giants. Next slide. We've also applied this to ourselves. So one thing that Google has is known for is running, you know, hyperscale, highly efficient data centers. And so we said, well, we're really good at this, but can we use machine learning? Can we use what we know to improve our own performance in data centers? And this was done a few years ago now, but we were able to save a ton of energy, 40%, by letting ML control the cooling in our data centers. Next slide. And then this is an example from Google Clouds. I thought it would be fun to show something about clouds. Airbus uses this looking at satellite images, and you could see that, you know, the way that this satellite image was viewed in the past was done by analysts, and they would have to look and try to make a determination of what in the image is snow and what in the image are clouds. And this is a very difficult thing to do, and after many years of experience and lots of examples, humans could do this in an all-right fashion. This is the kind of thing that's perfect for machine learning. Machine learners are able to identify that little spot in the upper right are actually clouds versus the other thing that's snow. Next slide. One last example is Ocado is a supermarket in the UK. They use natural language understanding, NLP, based upon, again, years and years of examples and research. Again, leveraging the data, leveraging the compute power, and then these improved frameworks to be able to understand that when somebody sent an email to them, whether it was an email that somebody was happy about, or email that somebody was frustrated, or a whole other type of sentiment that was in the email. And so they used it for triaging for customer service. Again, could have been done by a human, could have been done by an analyst. In this case, they had lots and lots of examples, and we're able to use that model to improve customer service. Next slide. So this first half of my talk, I really just wanted to give that sort of 30,000-foot view of AI ML, Google's place in it. Why is it happening today versus 5 or 15 or 20 years ago? And a little bit of a theoretical approach to AI ML. This last half, these last few slides, I want to talk a little bit about how you can apply AI to emerging companies, to startups, to early stage companies, to be super practical. Because I know a lot of people who watch these videos, who attend this seminar session, are interested in sort of the practicality. So, what can machine learning do for an early stage company? Again, the concept is machine learning uses examples to make predictions. So the key questions you have to ask yourself are, I think, these two. The first one is, what problems are you trying to solve? Do you have examples? Do you need predictions? These are really core questions. So what type of AI startup are you? Are you one that it's foundational, AI is your differentiation, or is it the cherry on top? Next slide. Let's talk about each of these, foundation and acceleration.
Hey, Dave,
Yes.
isn't this same perspective applicable to large companies who haven't started on their main AI deployments, because these are still examples for where you can start using AI if you haven't already?
Yeah, exactly. Exactly right. So from a project perspective, you have to ask yourself, is this project foundation, is AI foundational to it, or is it an accelerator?
Got it.
So let's talk about each of these. On the foundation side, you typically are building a system yourself. You have the data, you have the example, you've got the expansive data sets. You're going to leverage the community and the ecosystem and the amount of libraries and content that's available in the open source really matters. You're going to contribute to it and you're going to use it. And then the ability to scale and to do ML ops or scale your AI infrastructure really matters. If it's just an accelerator for your project, you can leverage existing systems and models. You don't have to, you typically have limited data. You don't have to invent it yourself. Access to integration with existing tools is what really matters, because you typically are a software developer, not a PhD in machine learning, and the ability to execute quickly with limited ML expertise is key. So let's talk a little bit about Google solutions on each of these. Next slide. From an open source perspective, TensorFlow is incredibly important. So if AI is foundational to you, I strongly recommend, and again, if you have this expertise, you're likely already using TensorFlow. The TensorFlow ecosystem, this is a set of libraries that were made available by Google. We took our own infrastructure, the way we train our own models, and made it available for anybody to use. 200 million downloads. You can see the numbers here. It's really quite compelling. Next slide. Similarly, from a infrastructure standpoint, we have TensorFlow Lite, which runs on devices, over 4 billion devices. We have something called Machine Learning Kit, or ML Kit, that has 500 million active users, and then TensorFlow JS, which has 50 million uses. And then Coral, of course, is our own custom-built hardware. Remember I talked about TPUs, TensorFlow processing units, that ran in our giant data center that were custom-built for doing inference at the edge. We now also have this available to do inference in the data center. We now have made them available to do inference on the edge. So edge TPUs, or what's been branded by Google as the Coral product line. Next slide. Vertex Ai is the infrastructure, the tool that Google Cloud has made available. We launched it in, I think it was May of this year at our big I/O conference. And it's a unified ML ops platform designed for data scientists and ML engineers, so that they can increase experimentation, deploy faster, and manage models. So what that really means is, as the last 4 years or so has gone, it's gone leveraging machine learning, creating and leveraging machine learning models in your applications has gone from something that only a PhD, or likely a PhD in machine learning would be the expert on, to something where software developers themselves can put their fingers on keyboards and include AI. So Vertex Ai, let's go to the next slide. There was actually a great session, I think, Ron, that you had with Dan Zarstasian back a few months ago, where he went down this whole process. I spent about a half an hour on Vertex Ai. This is sort of the one slide snapshot of what it is. It's an end-to-end system, from ingestion of data all the way through deploying the models at the endpoints, that makes it just easy for you to leverage these components. So this is, again, Vertex. We're talking about infrastructure, people who are driving the differentiation from AI as a differentiator. Go to the next slide. We'll talk about how a little bit how you can use AI as a cherry on top. So Vertex AI is not just for data scientists and data engineers, but you could also use pre-trained APIs, custom AI with AutoML, and then that piece on the right, which is the end-to-end Vertex AI for those data scientists and data engineers. So briefly, because this is sort of the most popular thing that people use, let's look at the pre-trained APIs and custom AutoML. So next slide. So the APIs and AutoMLs, this lets you use models that have been trained by Google already, but use your own data. So the pre-trained APIs for these things that I like to refer to at least as the senses, like bringing senses to your application, sight, language, and conversation. And then a little bit different, the structured data is a little bit different, but you can see vision, translation, speech to text, text to speech. So sort of across these areas, we've got pre-trained models that let you, as you build and deploy your applications, you don't have to be the ML experts. You just really need to bring your data and leverage our pre-trained and optimized models. So this is the cherry on top idea. This is the idea that your core application is doing X, but you want it to be really good at, let's say, conversation as a nice to, I'll say nice to have, but speech to text, text to speech, and dialogue flow, which is our chatbot infrastructure. Next slide. So this is a list of some of the accelerators with some descriptions. Not super excited about this slide because you can get this from our website, but again, as you saw on our last on the last slide, there are a lot of things that you can leverage. You can infuse your applications without being an AI expert. Next slide. I wanted to make sure that I provided the canonical, what does Google Cloud provide in AI? This is our portfolio. This is our most recent snapshot as of whatever it is, late November of 2021. Across the bottom, you see the TPUs and GPUs I talked about, which is the compute infrastructure for training. Then we've got what we call the data cloud, and this is all the different storage and data solutions that we offer, from BigQuery to through Looker and Spanner, and then the Vertex AI portfolio that I talked about, that Dan actually talked about a few months ago. So, and that has the AutoML and APIs, which are fantastic for that cherry on top, and then the ML ops and core. And this is for people who are really interested in driving that scale and differentiation through AI. And then sort of the newer things, I think, are the top two, the AI apps, platforms, and AI solutions. And if you were to ask me over the next 5 years where the most interesting things are going to happen in AI, it's around these two areas. So it's document AI, document understanding, for instance. Instead of just using AI for OCR and vision and looking at images and documents, this is really using AI to understand the context of the documents, to make predictions about those documents. So a contract, you can use document AI to understand when a contract might expire, even though it never says in the contract when it expires. It may say, hey, this expires in a year from execution date, and then it can infer and make a prediction about when that execution date is. So AI platforms and AI solutions is really the most exciting component, I think, of where AI is headed over the next few years. Not just us, but our peer group too, because this is where in the past AI was science. You could say it was a science project. It was really difficult to implement, and then today it's really practically easy to implement. You have things like these AutoML and APIs, but in the future, it's literally going to be applications that are just infused and delivered with AI infrastructure. Next slide. So to finish, you have to have a call to action. So here's my call to action. Number one, just do it. Don't wait. Get started. AI has, as I described at the beginning, when I was writing my program that to have baseball, it was very manual, time consuming. AI now can deliver, machine learning can deliver that in spades. It's just incredibly quickly. What problems are you trying to solve? These were the questions that I proposed earlier. Do you have examples? Do you have data? And do you need predictions? Do you actually need predictions? APIs are an easy starting point. Training is abundant. There's so many online resources now with Coursera and other places that it's really easy to get trained up. And then finally, if you want to see our products, our portfolio, that slide I showed earlier, it's cloud.google.com/productsai, and that will give you everything you need to understand what we offer and how to get started.